good evening to all. Today we are going to discuss week 6 content of environmental remediation of contaminated sites. The course instructor of this course is Dr. Bhanuprakash Velanki, and myself I am S. V. Chinnaswamy Naik and a PMRF scholar from IIT Roorkee. Today we are briefly going to discuss about overview of week 6 content. So that is course instructor mainly discussing about how can you get to know that whether the degradation of contaminants is occurring or not. So we'll decide the degradation is occurring or not based on um, three studies. One is by studying the historical data, the second one is by studying the lines of evidence, and then microism studies. So in historical data, what we will do, we'll check the past data of the particular contaminated site of uh, uh, of related contaminants concentration. So we'll study based on the previous study data, then we can conclude that whether biodegradation of particular contaminant site or particular contaminant is occurring or not. Similarly, lines of evidence. So lines of evidence, what we will do, so we'll just check the byproducts. So by considering the formation of byproducts, we will decide whether the biodegradation is going to occurring or not. So here mainly we are considering the hydrogen byproducts to identify the whether biodegradation is occurring or not. Similarly, and then finally the microism studies. So based on the microism studies, we can decide whether the degradation of contamination degradation of contaminant occurring or not. And then secondly, course instructor derived three derivations. So regarding by considering the uh, microbial activity, adsorption, desorption, advection, dispersion in a groundwater, and with only in groundwater with strata, soil strata. So if the more contaminant concentration in groundwater, what will happen, the adsorption will take place to balance to maintain the equilibrium. So uh, whatever the contaminants, some portion of contaminants move to the adsorbed onto the soil media and to get equilibrium. So similarly, once if the groundwater concentration is less than the soil strata contaminant concentration, what will happen, the desorption will take place to attain the equilibrium. Similarly, the concentration again will reduce due to the advection and dispersion as well. By considering these conditions, so we have derivations. So one by one, I won't derive all the derivations, because if you want complete derivations, please go through the regarding regarded videos. So here case 1, we consider microbial activity, adsorption and desorption. Only microbial activity, adsorption, desorption. So in the case 1, the formula is concentration at any particular time t, that is equivalent to initial concentration e power minus k dash t. So here again k dash, how will find out the k dash, that is k dash is rate constant by retardation. So again retardation formula, again we know the formula for retardation. 1 plus rho v, that is bulk density, and kp, coefficient of percolation. By epsilon, that is porosity. So but coming to the here, how we will find k star? K star will find by using Excel, and data given by using the data given in the question. So we'll use the Excel, we'll import the data into the Excel, and from the Excel by using the analyzer we will calculate the k value by fitting the model, by again by fitting the model, and we'll find the model concentration values, and then again we'll find the difference between the error. We will find out the error by subtracting the uh, data given value and model values. So we'll get the error again. To find to adjust the k star, to get the k star we'll have to find calculate the sum of square errors. So total sum of square errors will calculate, and by using the solver, by using solver in Excel, then we'll find the k star. Once you know the k star, then t already we know, then initial concentration might be given in the problem itself, so we'll directly calculate the concentration at any particular time t. So again, if you want to calculate rate constant directly by multiplying the retardation multiplied by k star, then we'll get the rate constant. So now moving into the second case, that is in second case what we are considering: microbial activity, adsorption, desorption, and advection as well. That is concentration at any particular time t, that is total concentration also you can say. Initial concentration into e power minus k tau, k star tau, k dash or k star, whatever. So here again for tau we know we have a formula for tau. That is retardation multiplied by horizontal distance and u by e. That is u is the velocity and epsilon is the u by epsilon is the porosity. Coming to the case 3, again how we will calculate the, if you want to calculate concentration at any particular time t. So what we will do, so again by just drawing the curve, will by fitting the curve, so we'll get the model concentration values, and from that again model concentration values we'll find out the error, and again from the error we'll find out the sum of square errors, and from that we'll get by using the solver again from the Excel, we'll know the value of k dash. From that k dash we can get a rate constant as well. So to find the retardation, the all values will be given in the problem itself to find the retardation, and again after that we will find the values for total concentration by using the tau values and k star values. So for case 3, so we have a formula that is in case 3 we have we derived the formula by considering the adsorption, desorption, advection and dispersion of contaminants as well. So here the formula will be bit lengthy, that is Ct into C naught e power P star by 2 P star So this is the formula to calculate the concentration at any particular time t in case 3 by considering the adsorption, desorption, advection and dispersion. Again here A represents one place 4k tau, or else we can square, actually it is square root of 4k tau. Here u star is the seepage velocity. We can just we'll get seepage velocity just considering the Darcy's velocity by porosity. Again here P star we can write it as so P star Plancke number you can write it as a seepage velocity, horizontal distance with dispersion coefficient. Again here tau we can write it as a horizontal distance by seepage velocity. And finally seepage velocity, how will get to know how will get seepage velocity. Q by A is the Darcy velocity. By dividing the Darcy's velocity with porosity, we will get the seepage velocity. So after deriving these three equations related to microbial activity, adsorption, desorption, advection, and dispersion of contaminants, and then uh, uh, in week six session, final topic, course structure taught in the recorded videos are case study. That is case study in Brooklyn site, US. So that is a case study about disposal of hazardous waste, included included a dense non-aqueous phase liquids NaPl. That is, so this site case main case is, that is disposal of hazardous waste included NaPl. So DNAPL you can say. And then contaminants are major contaminants how find is chlorinated ethane and ethane compounds. In remediation process they use this, that is hydraulic containment systems and the active source recovery system coupled with treatment of extracted water. So due to the potential of microbes to degrade various chlorinated compounds, so monitor natural attenuation appears to be the one of the additional remedial alternatives. So people use that monitored natural attenuation. So and then regarding these case studies, in the recorded videos we discuss site characterization, geological data regarding collecting the geological data source by allocations, and contaminant characterization data. So here they discuss. So that's all about week 6 overview. So we'll move to the previous year assignment questions regarding week 6. The first one is, the question number 1 is, consider the following data which shows concentration of caffeine in groundwater of an area irrigated with reclaimed water. So the groundwater of what they are asking, consider the following data which shows concentration of caffeine in groundwater of an irrigated with reclaimed water that depicts this depicts the infiltration of caffeine from the surface to the groundwater through the soil. Actually groundwater to soil, that is water zone. So and the concentration in different conditions they gave, like in irrigation water and similarly in groundwater, and detention frequency in groundwater percentage also they gave. So now what they are asking, caffeine which generally gets quickly degraded, which is present in high concentration in groundwater, which of the following may be the correct reason for this? See, they are saying that caffeine present in groundwater caffeine present in groundwater with high concentration which is get degraded quickly. So what, by observing data also we can see that in irrigation water the caffeine concentration is, if you consider the maximum limit, so that maximum value that is 25,000 2,58,000 nanogram per liter. So but when it comes to the groundwater, again it is good amount of caffeine is released into the groundwater, leached into the groundwater, that is around 14,000. So it shows that what could be the reason to transfer to leach the caffeine compound from the irrigation water to the groundwater by passing through the soil strata. So here it shows that the compound, caffeine compound is highly hydrophilic. So what are the options they gave? So what they're asking, which of the following may be correct reason for this? So one reason is they're giving caffeine is highly hydrophobic compound. Caffeine is highly hydrophilic compound. Most of the caffeine gets absorbed in water zone. So we can conclude that by seeing this concentration of groundwater, irrigation water, and again the condition they mentioned that whatever the high concentration caffeine present in groundwater which is gets quickly degraded, that means it is the caffeine is highly hydrophilic in compound, hydrophilic compound. There is a common data given for question number 2 and 3 as well, so we have to use this data for both question number 2 and 3. So what they're saying, so groundwater at site was contaminated with triclosan 5-chloro to 2,4-dichlorophenoxy phenol, an antibacterial agent widely used in disinfectants and personal care products. Samples were collected at 4 different locations in the direction of groundwater flow, starting from the location A. So, okay, from the starting from the location A, the concentration of triclosan given in nanogram per liter. So, as with respect to distance, uh, different samples were collected at different locations. So, locations and distance given here. So what they are asking in question number 2, based on the above information, what can you infer? So we can see that as distance goes away from the initial sampling site. So what can we observe, like concentration of triclosan is decreasing, right? So what they're asking, based on the above information, what can be the what can you infer? So natural attenuation of triclosan is probably taking place. Attenuation due to adsorption onto soil is likely to occur. Triclosan is a volatile compound. Actually triclosan is not a volatile compound. So now answer for this question number 2 is, because as concentration decreasing as we go away from the initial sampling point, so we can conclude that natural attenuation of triclosan probably taking place, and similarly adsorption also we can accept likely to occur. So answer for this question 2 is A and B. Which of the following are correct inferences from the above information? Question number 3. Which of the following are correct inferences from the above information? So same data we have to use for question number 3 as well. So what they are saying, destructive attenuation of trichloroethane is taking place. Trichloroethane is highly resistant to degradation. Monitored natural attenuation can be used to treat sites contaminated with trichloroethane, and monitored natural attenuation is not ideal technique to treat sites contaminated with trichloroethane. So what will be our answer by considering the uh, common data given for question number 2 and 3. So that is, so destructive attenuation of the trichloroethane is taking place. That is I guess microbial activity we can expect. So because as concentration from point A to point D is decreased drastically, so we can expect natural attenuation also, because trichloroethane can be taken by the degraded by the microorganism. And similarly we can expect uh, monitor natural attenuation can be used to treat the contaminated site with triclosan, because as we seen in the case study, so for treating the triclosan, so monitor natural MNAs, so natural monitor natural attenuation can be best suitable option for treating the triclosan, we can conclude from the case study. So answer for this question is A and B, sorry, A and C. Then question number 4. So question number 4, they direct, it is a direct question. So what they are asking, they calculate the retardation factor for the following data. So porosity given, that is epsilon, and bulk density given, that is rho b, and organic fraction coefficient KOC, and fraction of organic carbon FOC. So now retardation factor formula is direct, it's a simple direct question. So that is 1 plus rho b kp by epsilon. So again kp, how can we rewrite the kp, that is ka into FOC, KOC into FOC, that is organic partitioning coefficient multiplied by fraction of organic carbon. So if you calculate this, if you do this calculation, so we'll get the retardation factor, which is 8.8. So answer for this question is retardation, that is 8.8. Question number 5. So with reference to the Louisiana case study, so give reason why monitored natural attenuation was considered viable option for removing the dichloroethane. So one the what they are giving option: low nitrate concentration, yes, anaerobic conditions, and presence of hydrogen and ferrous. So yes, because of the presence of low nitrogen concentration, so and anaerobic conditions and presence of hydrogen and ferrous. So what are the main reason to prefer the monitored natural attenuation in case of uh, Louisiana case study? So as we discussed earlier, like in aerobic process, so oxygen will be act as a electron acceptor. But here in anaerobic process, so nitrates will act as a electron acceptor if there is any nitrate present in the similarly ferric and hydrogen ferric also Fe3 plus also act as a electron acceptor when there is no oxygen. So what can we conclude that because of low nitrogen concentration also we prefer uh, MNTs like monitor natural attenuation MNS. And similarly in anaerobic conditions, so of course in anaerobic condition, so presence of presence of if in anaerobic condition presence of nitrates or oxygen will be less, so what will happen, the microorganism will start degrading taking degrade the dichloroethane. And similarly presence of hydrogen and ferrous compound. So option for this question is A, B, C. So coming to the question number 6 and 7, again common data given for both question number 6 and 7. So what they are saying, consider the following data obtained for a plume contaminated uh, with leachate from a waste pit that contains degradable organic matter as well as trichloroethane. The following data describes the condition in this aquifer. It is they gave the effective porosity and similarly bulk density, organic fraction of carbon and organic fraction partitioning coefficient of trichloroethane and hydraulic conductivity, hydraulic gradient. So from these two what we will get, we will get the velocity, that is V is equal to Ki. Darcy's velocity we can say, and average groundwater velocity, that is Darcy's velocity 20 meter per year also they give, and then observed concentration of trichloroethane at sample locations are given below. So different locations and their distance from uh, initial sampling aside with respect to different location, then their distance they give, and then groundwater concentration of trichloroethylene they give. So assuming steady state flow and plug flow reactor. So steady state flow we already derived the equation for steady state flow. So by in steady flow with respect to time, the changing concentration will be zero. So what they are asking now, determine the model concentration at location C. So at location C they are asking model concentration. So at location C the distance is 150, that is horizontal distance, and trichloroethylene concentration is given data is 0.58. So how we will calculate? So I'll go to the Excel. So if you see the Excel, I just wrote down the values given in the question. So distance and concentration as per question they give. So on retardaction factor, I calculated based on by using the uh, data given. They gave bulk density and organic fraction and coefficient of organic fraction they give, and then I calculate the seepage velocity by they already gave the Darcy's velocity. By using that, I calculated the seepage velocity. So and tau values. So tau values for different concentration at a particular different distance, tau values will be varies, because in tau values we are considering the uh, formula, that is Rx, retardation factor into x by seepage velocity. So for that, what we have to we have to calculate the tau value for each concentration. So we calculated tau value and initial concentration given, that is 1.3. So from that we'll calculate the k value. I calculated the k value. So in the beginning I consider the k value is 0.095, but after by using the solver, uh, I got this k value at is 0.095. So the model value I calculated, this here the model value I calculated, and then error from subtracting the concentration value from the model value. So I got the error. From that again I calculate the sum of square errors. From that again sum square errors. From that sum of square errors I calculated. After calculating the sum of square errors, I use the solver tool in the Excel, and from that I get the k value. So that is k nothing but k dash value. So k dash value I got. So once you know the k dash value, you can calculate the uh, C concentration at any particular time t. So now here k value is 0.095, right? So I will calculate the concentration at location C. They ask. Yes, sir. No, sir, I am in the lead. No, sir, I'm doing, I'm on the process. I'm talking with fine, fine. It is around 5,000, sir. Yes. Okay, sir. Okay, sir.
अरे पूरा ऑन है। अरे बात क्या करते देख रहा हूँ मुझे किसी बात अरे तो लाइट करता हूँ तो वो दिखेगा। अरे नहीं लाइट करता हूँ लेकिन मैं दवा नहीं खाता है लाइट भी सेकंड ठीक है ठीक ठीक स्टूडेंट्स को वो आपने टेक बार आपने दिया था उसमें स्टूडेंट ने लिया अच्छा वो टेक एक्चुअली मेरा टेक था है ना नहीं तो अभी वो आपने स्टूडेंट्स को वो रिक्वायरमेंट होगा भी था कि तो मेरा आपका अभी बढ़िया से लिखो वो सुबह पानी रखा हुआ है हमारा सारी कैबिन की उनके पास सर की मुझे आप शेयर करेंगे या सर की लिखोगे अच्छा वो हमारा बहुत दिया है हाँ वो सही रहता है नोट्स का कोई प्रॉब्लम ठीक ठीक आप इस बात को लेकर हमें बताइए हमारा। आप कीजिए, आप ऊपर आ जाइए, 2 मिनट में आपको समझ आएगा। ठीक ठीक ठीक।